Okay, so far we've done the Metropolis and the Metropolis Hastings algorithm. And, last week we looked at kind of the Metropolis algorithm for deciphering some text, and I hope you guys enjoyed that example and got to see the Metropolis algorithm in context. But, I want to just take a moment and just kind of pull back and talk about, the big idea of kind of the course and the whole MCMC thing, right? So the big idea is there is a probability distribution that's of interest to us, okay? We've got some target distribution. We have a target probability distribution that is of interest. So this is the thing that we want to know. But the target distribution is too complicated for direct analysis. Okay? So the methods that you've learned in your Stats 100B class, they're not enough to get us through here. Okay? So target PDF, target distribution is too complicated. All right, so instead, in the Monte Carlo methods class, we decide to settle for a representative sample. Okay, so we'll say, all right, I can't figure out the target distribution. We will settle for a representative sample. Okay, and so prior to midterm 1, we covered methods like inverse CDF and rejection sampling, and these are ways for us to get a representative sample, right? So we have inverse CDF, rejection sampling, can get us a representative sample. And these methods are fine, and mathematically, if we let n go to infinity, these will give us representative samples, and they'll work. But we don't have time equals infinity, and so some of these methods are very inefficient, right? So we said, rejection sampling or any of the other methods can sometimes be incredibly inefficient, especially if you're trying to sample from, I think this was an exercise in the homework where you sampled from like -20 to +20 using uniform, and then you use rejection sampling to figure out what values to accept, and you're only accepting like 10% of your values, which is a waste of computational power, okay? And other things in higher dimensions may be even more inefficient, right? So in some cases, these methods, like rejection sampling, so although theoretically they work in the long run, can be inefficient, sometimes grossly so, can be inefficient, and sometimes it may not even be possible if we do not have a normalized PDF. Normalized means the thing integrates to 1. So we might not have that, right? In one of your homework examples, it was important to find that normalizing constant. Otherwise, your estimate would be off, right? Off by like 2%. And okay, and so in these cases, we resort to MCMC. Like the Metropolis algorithm, okay? And Metropolis Hastings algorithm, okay? And so far, we have looked only at target distributions of one random variable, okay? So all of our examples so far examples of MCMC so far have been for target distributions of one variable. So, you know, for example, we were trying to, you know, the distribution of the kind of proportion of kind of green M&Ms. All right, so that was a beta distribution for the proportion of green M&Ms. Maybe we were looking at the distribution of the rate parameter lambda for like the exponential data and things like that. And even the example where we are deciphering text, we have, it's one letter mapping, right? A distribution over letter mappings. It's just one parameter, and it's the letter mapping. It's difficult to express, but it's a distribution over letter mappings. It's just one thing to vary. Okay, and so today I'll kind of introduce some concepts for distributions of kind of joint distributions of multiple random variables. We'll take a look at kind of like the most simple case, and then we'll discuss the Metropolis algorithm in that context, and then on Wednesday and stuff we'll look at better algorithms here. Okay. So what do I have? Okay. So we'll look at distributions of kind of multiple random variables. All right, and we'll do a kind of a Bayesian example, like a simplest multivariate Bayesian example. And this will be, we'll look at two beta distributions. So our textbook example is that we have two coins, and we want to find the joint distribution of the kind of the probability of landing heads for both coins. Okay, so coin one has theta 1, and coin 2 has theta 2. theta being the probability it lands heads. Maybe it's 0.5, maybe it's 0.9, maybe it's something else. Okay. Or, you know, another silly example would be, you know, you've got 2 buckets of M&Ms. And, you know, maybe they have different proportions of green M&Ms, and you want the joint distribution of all of these things, okay? So maybe all right. So these are especially silly to kind of bring up and talk about MCMC and Bayesian inference, because both of these cases, the joint distribution, the 2 distributions, like the coins are independent, the buckets are independent, so the joint distribution just ends up being a product of 2 independent distributions, not a big deal, and we can easily simplify these things, and we'll work through the math, but this is, again, it just serves as an illustrative example. We'll look at kind of the simple case, and it'll be easy if we understand how it works for joint distribution of independent variables. It's not a crazy leap to go into a joint distribution where there is covariance between the variables. Okay, and you know, because the same concepts hold. It's just now we have covariance between variables and not just independence, right? So again, you know, these are silly. These truly are silly because, you know, the analytic methods are easy. Because the variables are independent. Okay, but we'll study this as a joint distribution, and these concepts can be generalized for other situations. Okay, we'll study this illustrative example to help us in more complex scenarios. Okay, all right, so, you know, for example, maybe the distribution for coin 1 is a beta distribution that it goes from 0 to 1, and maybe it looks like this, okay? And maybe the distribution for coin 2 being you know, another beta distribution from 0 to 1, maybe it looks like this. Okay, let me draw that. Okay, and thus the joint distribution, just being a product of the 2, may look something like this, right? Where coin 1, if you look from you know, this perspective, it would look like this. And then if you, for coin 2, if you know, if your eyeball is right here and you're looking at this perspective, it looks kind of like this. I don't know if this picture makes sense, but you know, you got this hill where from one angle it looks like this, and then from the other angle it looks like this. It's just a joint, we're just multiplying the two together. It's not, it's easy in this context. Okay. So the distribution for coin 1, I guess this would be theta 1 comes from here, and theta 2 comes from there. And then the coordinates, theta 1, theta 2, come from this joint distribution. All right, is this okay? Questions before I move on? We're good, okay. All right, so in this case, we've got two parameters. We've got the proportion for coin 1, which in this case is theta 1, and we've got a proportion for coin 2, we've got theta 2, and then what we want is we want the posterior distribution, or I should say posterior joint distribution of theta 1 and theta 2. Theta 1 and theta 2 given the data D. Okay. So we want the distribution of theta 1 and theta 2 given our data D, and according to Bayes' rule, what will we have? So this is the likelihood, the probability of the data given theta 1 and theta 2 times the prior divided by the probability of the data, right? Okay, and then the bottom, the probability of the data, this is just the integral of the numerator across all possible values of theta 1 and theta 2. Okay, so the denominator is going to be the integral of the numerator across all possible values of theta 1 and theta 2. And so, mathematically that becomes probability of the data is double integral of the numerator, d given theta 1, theta 2, times the probability of theta 1 and theta 2, the prior, all over all possible values of theta 1 and all possible values of theta 2. Okay. And again, this just becomes a constant with respect to theta 1 and theta 2. And again, it's just a normalizing constant. Its only purpose is so that the whole thing integrates to 1. No other purpose. Okay, so that's what we want. So we're just going to look at the the two pieces in the numerator, and talk about what we end up getting there. So so our data will be from coin 1. We'll have Z1, which is going to be how many heads. So we have Z1 heads out of N1 flips. And then for coin 2, we'll have Z2 heads out of N2 flips, okay? And so it's like you've got a quarter, and then you want to know does the quarter land heads at a different rate than my penny? And you flip the quarter 100 times and you get 53 heads, and you flip the penny, 50 times and you get 21 heads. And you go, oh, is my proportion different? Yeah. I don't know. This is dumb, but this is what we're going for, right? Okay. So Z1 is just going to be the sum of your y1 sub i's from I equals 1 to n1, okay? Where y1 sub I comes from a Bernoulli with parameter theta 1, right? And so y1 sub I is either going to be a 0 or 1 as determined by your theta 1 parameter, okay? And then, z2 is the same, just replace the 1s with 2s. Okay, and then so, your the likelihood of the data as a function of theta 1 and theta 2 so this is going to be the probability of the data given theta 1 and theta 2. This is going to be the product between our y1 sub i's given theta 1 and theta 2 and the product of your y2 sub i's given theta 1 and theta 2. And so this is just, a Bernoulli likelihood. And so is this, also a Bernoulli likelihood. So here we get the product of, so y1 sub I is going to just be 1 or 0. So we got theta 1 raised to the y1 sub I times 1 minus theta 1 to the 1 minus y1 sub I times the product of theta 2 to the y2 sub I times 1 minus theta 2 to the 1 minus y2 sub I. So those are just your Bernoulli likelihoods, and then you got the product of all of these things. So you're going to get theta 1, and then you sum up all of these, and that becomes z1. And you get 1 minus theta 1, and then you sum all of these up, and you're going to get n1 minus z1. And over here you get theta 2 to the z2, and over here you get 1 minus theta 2 to the n2 minus z2. Okay, and it's kind of silly, but it's just a product of Bernoulli likelihoods, and that's because our data, the two coins are independent. Like, if we wanted to, we could just split them and solve these problems individually, and just say, like, here's one coin and let's look at this. Here's another coin and let's look at that. Yes, we could do that, but the whole point of this is, what do we do in a joint distribution situation? It just so happens that they're independent, and so that this feels very silly, but what we're doing here easily applies to situations where there's covariance, where you'd probably have some kind of covariance term in the data here. Just not in our example right now. Okay, so this is our likelihood. The prior distributions, which is theta 1 comma theta 2, I guess prior joint, the joint prior distribution, or the prior joint distribution, whatever you want. This is just going to be a product of beta distributions. So we will have beta distribution with A1 and B1, alpha 1 and beta 1, and then beta distribution with shape parameters A2 and B2, which become theta 1 to the a1 minus a1 minus 1 times 1 minus theta 1 to the b1 minus 1. And over here we've got theta 2 to the a2 minus 1. And over here we've got 1 minus theta 2 to the b2 minus 1 times some normalizing constant. So let me just say it's proportional to this. Is that okay? All right, and then so your joint posterior distribution is going to be proportional. So this is probability of theta 1 comma theta 2 given the data. This is proportional to the likelihoods times the prior. Okay, let me just copy and paste from the previous slide. Where is it? Lecture 2, week 8. So the previous slide was this. I just copy and paste this. Oops. Copy that. Okay, so we'll have this times, let me just get this one, and I'll copy this, a prior, okay. So we have that. And then, okay, so all of this, so everything's proportional, technically. All right, so this is going to be proportional, and so we have to just combine all of the terms. So I got theta 1, and I do z1 plus a1 minus 1, 1 minus theta 1 to the n1 minus z1 plus b1 minus 1, theta 2 to the z2 plus a2 minus 1, 1 minus theta 2 to the, and I add these two terms, n2 minus z2 plus b2 minus 1. Sorry. Okay, and then is that all right? I'm just adding like terms, coefficients of like terms, and then this we can say, all right, well, if that's the form, then this just becomes a product of beta distributions, which is going to be, you know, z1 plus a1 comma n1 minus z1 plus b1 times the beta distribution PDF of z2 plus a2 comma n2 minus z2 plus b2. All right, and this was, again, it just turns out to be the product of two independent beta distributions. So we could have, again, said, well, it's independent, so we're going to just look at these two things separately. But again, we're just treating it like a joint distribution, and this is our joint distribution at the end of the day. All right, is this okay? And so this would be what our probability of theta 1 comma theta 2 given our data would be. And that's our posterior. And if we were to do the Metropolis algorithm, this is the posterior distribution. This is what we would be using to calculate our acceptance ratio. Okay? All right, so let's just talk about what the Metropolis algorithm looks like for a multivariate distribution. Okay? And basically, the process is exactly the same as the Metropolis algorithm, same as the Metropolis-Hastings algorithm. The only difference, again, Metropolis-Hastings doesn't have a symmetric proposal. Metropolis algorithm does. And so, let's just do this. Okay, so, how do we do, say, the Metropolis algorithm? For a multivariate distribution. All right, so just like before, you start at an arbitrary location. This time, because we're trying to estimate two random variables, our location is going to be two-dimensional. So we've got a coordinate. So start an arbitrary location. This time, theta 1 and theta 2. We've got a coordinate. And then we will propose a new coordinate. All right, so we'll call this theta 1 prime and theta 2 prime. So this will be some new coordinate that we propose, and this comes from a proposal distribution. So because we're dealing with a multivariate distribution, our proposal distribution also needs to be multivariate. Okay, so our proposal needs to be multivariate. Okay, so let me just give you some examples. So one would be the multivariate normal. Okay, the multivariate normal centered at what? Your current location, right? So the unidimensional case for the Gaussian proposal was a normal distribution centered at your current location. Here we just make it multivariate by saying we got a multivariate normal centered at your current location. And so we would say in this case, our values theta 1 prime and theta 2 prime come from a multivariate normal where our mean vector is going to be equal to our current value, current location, theta 1, theta 2, and then what? Well, what should our sigma matrix be? Well, it could be anything. It could be anything. It probably makes sense to use the identity. This would be a two-dimensional identity matrix, because then your values would be independent, but it doesn't have to be. You could have a proposal thing that comes from some ellipse rather than a circle, or whatever else you want it to be. Okay, so that's a multivariate normal centered at your current location. What else could be? So I think in your homeworks you had the multivariate, not multivariate, you had the normal proposal distribution. What other kind of proposal distribution do you have? A uniform one, right? So what would a uniform look like in the multivariate case? So we would have a multivariate uniform. And so this would just be kind of theta 1 and theta 2 prime would come from basically centered at your current location, so it'd be uniform from probably your current location theta 1 minus 1 to theta 1 plus 1, and uniform theta 2 minus 1 comma theta 2 plus 1, right? So the multivariate Gaussian, this is your center location, and you're kind of drawing values on this space. And then over here, if this is your center, you're just drawing a random point from inside a square where each side is. So this is your coordinate theta 1 comma theta 2, and right here is your coordinate. So you just have some distribution centered there, right? Okay. So so you have this, okay. And then, all right, so Metropolis algorithm. So you propose a new value, theta 1 prime and theta 2 prime. And then what's the next thing we do in the Metropolis algorithm? We have to calculate an acceptance probability, right? Okay, and the acceptance probability is going to be exactly what you think it is. So what do you think it is? So we're going to start off with the word minimum. Minimum between what? 1 and probability of the proposed value. So probability of theta 1 prime, theta 2 prime, divided by the probability of your current value, theta 1 and theta 2. Yeah. Okay. And you know, if it's Bayesian, okay, so if Bayesian, you know, we are using basically our posterior distribution, theta 1 comma theta 2 given the data, okay? And then, and you know, because of the ratio, we do not need to calculate the normalizing constant probability of the data, right? So if it's Bayesian, because our acceptance probability is the ratio of these two things, if there's a normalizing constant, it cancels out in the numerator and the denominator. We don't actually have to calculate it. And then, of course, if it's Bayesian, we're going to be using the posterior distribution to evaluate the to figure out what our acceptance probability is. Yeah. Okay, and then of course, after you get your acceptance probability, you draw U to decide whether or not to accept, right? Decide to accept, or I should not accept, to decide to move or not, right? And if you move, then this becomes your new value. And if you don't move, you stay put, and your current location just becomes another value inside your sample. I hope this feels okay, that this doesn't feel like a huge leap from what we've done. This is the multivariate generalization, and it should feel very similar, except, you know, now we have multivariate proposals, okay? And of course, these are just simple symmetric multivariate proposals. And if you want to do Metropolis Hastings, you don't have to have a symmetric multivariate proposal. You could have one that's not symmetric, and then you would adjust your acceptance probability to have that kind of the proposal distribution ratio will also be thrown in there. Okay, so this is fine, but even this can become inefficient. Even the Metropolis algorithm can become inefficient because when it was unidimensional, you're just proposing a value along the line, and we're looking at, is this more likely or less likely? And if it's less likely, then you might reject it. Okay. Now, in a two-dimensional, we're proposing a value in a kind of a square or in a plane, right? And so if you imagine, trying to hit a target, it's a lot harder to hit a target in 2 dimensions. And then if we go to 3 dimensions, now we're proposing a value inside a cube, and it becomes even harder. And then as we get into higher and higher space, it gets harder to kind of quote hit whatever target we're trying to hit. Because let's say we have a joint distribution. Our target distribution is a joint distribution over 7 variables, and we're using a multivariate proposal distribution. And maybe the multivariate proposal proposes good values, likely values for 6 of them, but 1 of them is really unlikely. Okay, and because that one value is really unlikely, that entire coordinate of 7, location of 7 coordinates will get rejected, or is likely to be rejected because the acceptance probability is going to be very low. Okay, so even though this is good, we can still run into problems when we have things that are of high dimensionality. Okay, and so on Wednesday we will take a look at something called the Gibbs sampler that helps us avoid this problem of having kind of a low acceptance probability when we have a high dimensional proposal distribution. Is that okay? Are there any questions? Okay, so we will we'll end here for today. We'll see you guys on Wednesday, and we'll look at the Gibbs sampler, which tries to solve this problem of working in high dimensions.